Hello, yeah, this is on. Good morning. I guess this is the final day of the summer school, and we are going to jam your brain with some more cool ideas. So this is a session on big data. Really, how are we utilizing all the data that we collect? So I have really two great speakers here. One of them hasn't arrived yet, but you have seen him yesterday, Andres Munoz and Ryan McGranaghan at the back. Both of them are actually summer school and Eddy alums. In my way of thinking, it's the full life cycle of a heliophysicist. Start with summer school, graduate to IID fellow, become faculty, researcher, and future leader. But they are also mentors in another program I'm running called Frontier Development Lab, and that's what I'm going to give you a brief description of. And they've been doing that also for a couple of years. So I hope you learned something from what we are doing. This is not my area of expertise, and kind of see how you might apply this to future endeavor. So very briefly, I kind of came into the world of AI, I would say, in a very interesting way when I went to NASA Ames and embraced it when I saw what was possible. And I call it my Brave New World, which is actually a novel written in 1931 by an English author called, known as Aldous Huxley, and it's a dystopian view of the world. It's negative utopia, and what I am trying to communicate is that the vision we could develop with AI can be very different. It could be a utopian view of the world. It's AI for good, even though I know that AI actually lands up getting a very bad rap. So let's get started, and I'm just going to start warming you up. I know many of you are very familiar. You have used AI/ML tools, but not all of you. And so when I do this talk, sometimes I kind of give you a perspective from someone like me who just knows enough to be in trouble. So what's the point of application of AI? The fundamental point is that we can now digitize anything we want. It can be a cat, it can be a human face, it can be DNA, or a scent, for example. And once it's math, we have labeled examples and we can train a neural net, and that's what you're looking at here, numbering stuff. That's kind of at the heart of what we do. And in this case, what we are trying to do, the picture that you're seeing there, is we are training a neural net to recognize meteorites, which generally have kind of different appearance from rocks because they haven't been softened by erosion. And we are trying to kind of really look at rocks versus meteorites. And after we have looked at, say, 26,000 images, we need a lot of images to apply AI. The neural net is trained and it becomes what's called an inference model, a learner. And it's like a probability matrix in that sense. And it can actually identify a meteorite from a rock. And this is something we actually put into practice in the very first Frontier Development Lab experience. So this is actually, once we have an inference model, what we can do is we can let loose on the real world a meteorite drone, which actually collects these meteorite samples. And if we have these samples collected, then we can use our inference model on that to diagnose whether it's a meteorite or a rock. And scientists have a lot of interest in knowing this because this kind of gives them an idea of the composition of the asteroid, where did it come from, whether it's a piece of asteroid or just a meteorite from our local environment. So in this case, the inference model was very successful. It found 16,000 possibles, but also it actually found the meteorite in this particular case with only 2 false positives. And these are very important, time-consuming activity. Applying AI makes a very big difference. So that's kind of sort of the 101 of AI. You can train a neural net to learn to recognize and digitize things with a very high degree of probability. That's just kind of statistics, one way of thinking about it, because I know people get afraid of the black box aspect of AI. But where it gets really interesting is when you don't have training data, or you are actually working with 3D or multidimensional data, which is why this GIF is absolutely awesome. Once an inference model is trained, it can see things that human eyes with our limited mammal senses cannot, and that's what we are after. So what is NASA really doing with its big data, right? That's the big question. And let me show this. We are collecting about 2 gigabytes of data every 15 seconds from over 1,000 of our spacecraft. And this is where I think AI comes in. And you heard from John Grunsville yesterday afternoon about the Science Mission Director at Science. So very many different kinds of science that we pursue. So this is, the frontier development came into existence as kind of combining deep learning with deep science, public-private partnership, which essentially leads to new synergies at NASA. Now, space science is data heavy, and one of the most important thing is that what we find that the performance of the new AI tools, deep learning, essentially is not halted when we supply huge amount of data, when all other statistical models seem to plateau. So deep learning has some cool aspects about it. These are the players, and I'm not going to talk about it because I think both Ryan and Andres will give you a little bit more about how the FDL program is run with early career PhDs. The teams are very interdisciplinary in nature. It's over 2 months in summer. As you are seeing, it happens in the Silicon Valley. We partner with the SETI Institute, bringing these teams together, and it leads to many different kinds of possibilities. There is process improvement, there is actual discovery in the topics we choose, and it's not all heliophysics. It's all aspects of science and exploration. There is actual understanding, and there is, of course, exploration. Let's not talk about that. These are the various tool sets we have. This mouse is very sensitive. And these tools are what we are applying to very many of our topics. The takeaway from here for many of you practitioners is that the AI toolbox is already too broad and deep for most scientists. Similarly, it's hard to know the tools unless you have domain expertise, and that's why we bring these two components together in a team, and interdisciplinary is key. Data scientists really don't know all the pitfalls, and domain scientists don't know the full toolbox. So that's kind of an approach to work on. And I'm going to end on that note and have Ryan come over and give the first presentation of the two-part series for the big data approach to, I guess, more or less heliophysics is what we might be talking about now. Thank you, Ryan.
All right, thank you, Lika. And thank you, Kendra and Nick and everyone who has organized this really fantastic event. It's something that I took part in. It was really impactful for me, and so I'm glad to see that everyone here has had such a good and fulfilling past week. I've been really excited when Lika reached out to me to come back and give a lecture because what I've been doing lately has been really trying to shape and understand what I believe is a new frontier in the field of space physics and really across science. Lika made the excellent point that a lot of the things that I'll talk about really cut across disciplines. and they're a natural way for different disciplines to interact and communicate. And so one of the themes that I'd like to illustrate today is radically interdisciplinary collaborations are possible when we look at this through the lens of methodology transfer and data science. And so I want to illustrate that new frontier and how each of you can contribute to shaping that new frontier and envisioning what that looks like. And so really what I want to do today is kind of craft a narrative around data science and the potential and really the need for data science in each of the scientific fields that we are involved in. And I'll do that specifically through the lens of heliophysics, but it's going to really speak to and create messages that exist across all of these fields. So one of the terms that I'll use that I think kind of helps people think about this a little differently is anti-disciplinary, where you see all of these prefixes attached to disciplinary, like unidisciplinary, multidisciplinary, transdisciplinary. I think a new approach to that is anti-disciplinary, where a lot of this work that we're trying to do now and the discovery that we need exists in spaces between fields that we can't accomplish within any one domain particularly. So I will come back to that as kind of a lasting message from this talk. But really, this talk is meant to kind of give you an overview of some of the things, some of the aspects of the new frontier. It's meant to not load you up with information, but really give you the tools and the questions and the ideas to have a rich interpretive approach to this new frontier that we're talking about. But I realize that a lot of people in this room probably don't have any idea who I am, so I wanted to give a little bit of background on myself, and I think the trajectory that I've followed in my career might be illustrative for some of the things that are on your mind now and how you want to approach this new frontier. So who am I? I'm Ryan McGranaghan. I currently work with a company called the Atmospheric Space Technology and Research Associates, and that's located in Louisville, Colorado. But like the radically interdisciplinary theme that I've been talking about already, I work on a number of different projects. So I actually live in the Washington, D.C. area, and I work at the NASA Goddard Space Flight Center there. I work with Lika at NASA headquarters pretty frequently, and then across the landscape there as well. But where did I start? I came here to the University of Colorado in 2011 and did my PhD, and I arrived working on interplanetary trajectory design and optimization. And when I got here, I became immersed in this aerospace engineering sciences department at CU. And that was kind of a really unique thing for me at the time, where they were fusing together the sciences and engineering. And so I started to get exposed to the space environment and how heliophysics and solar energy impacted all of the things that I was trying to do. And so I started to bring these different fields together, and that was really kind of my first step out into that interdisciplinary space. After I graduated with my PhD, I went to Dartmouth College, where I was a visiting faculty member, and this kind of led me to grow some of these ideas that I was thinking about. While I was there, I designed and offered a graduate level course in data assimilation and data science, and it was really illuminating because we had students from every corner of campus attend that class and take that class. We had engineering students, we had physics and astronomy students, applied math. We actually had humanities students as well who were trying to figure out how to use data more effectively. So it was really eye-opening for how cross-cutting a lot of these methodologies are that I'll talk about. And I took that information and those lessons to the Jet Propulsion Laboratory, where I went as a Jack Eddy Fellow, and it was a fantastic experience. It was a wonderful program because it gave me the autonomy to kind of go to JPL and explore the lab and really get involved in these departments that I normally would not have been able to if I were tied to a specific project. And so it was really nice because I got to work with the data science working group there, which I think is one of the most forward-looking groups in this space, led by Dan Crichton and Rich Doyle. And if you're interested, I'm happy to connect you and put you in touch with some of those materials. But it was really wonderful to work with them. I led the first heliophysics-focused pilot program for the data science working group, and that was a program that I'll talk a little bit about. But it was a really radically interdisciplinary program where we involved earth scientists and computer scientists and embraced some of the ethos that Lika was talking about with the Frontier Development Lab program, where you really have to bring these groups together in these teams to gain the expertise with the growing scale of science that we face. After JPL, I moved to Astra, as I mentioned, and am starting to kind of grow some of these ideas in a data science working group of my own, and trying to reach out and interact with individuals at NASA and some of the initiatives that are happening there. But along the way, I kind of have developed another approach, another perspective on something that's really important in this field, and that's communication. I think it's really important that we reach out to the people in unique ways, try and reach them and let them know what we're working on so we can create these ties that allow us to do interdisciplinary collaboration. So a few of the experiences that I've had, I was able to give a TED Talk on some of this material. That was a really fun thing to do. I've been on some unique stages like the NASA Hyperwall, which is just kind of this massive wall of TVs you design this special presentation for, and it kind of screams messages at people. It's really fun. And then I actually have a new podcast that I've been working on, and actually Lika was the first guest on that. We kind of talk about some of the thought leaders in these different spaces, their career trajectories, and try and understand the pivotal moments. So if you're interested, give that a listen. But outside of work, I spend a lot of time here in Colorado, so I absolutely love the outdoors. Spend a lot of time backpacking, so it's nice to be back for a few days. And then I have 2 brothers and a sister. I'm the youngest of 4, and we're all kind of kooky Packer fans. So we have that going on. But what I wanted to talk about today, I really wanted to structure in kind of 3 specific points. And I wanted to build that around 3 questions. So the first is to kind of clarify some of the buzz terms that exist in this field of data science, which I realize data science is itself a buzz term. So I want to start with what is data science and why is now a critical time and really a nice opportunity for each of you who are at a nice point in your career to embrace some of these things. Then I want to add some substance to that. I think we really learn by seeing the fantastic use cases. So I wanted to look at what can we learn from those fantastic use cases that address the full data life cycle. And then finally, I want to kind of have a forward-looking approach because this is very open-ended and give you some of the questions by looking at how we can shape the new frontier. So I'll start with what data science is. And I mentioned I'll speak in terms of heliophysics. This is our heliophysics observational system, the NASA heliophysics observational system. And you can see that we have observations coming to us from every component of our interaction with the sun 24/7. We have a number of instruments on Earth and in space that allow us to do that. So what that indicates is that we have a drastically changing data landscape. And that can be described by this buzz term, big data. I think there's a little bit of a bias associated with big data where people think it's just massive volumes, but it's much more nuanced than that. And big data actually speaks to a number of different V's in this landscape where you have the growth in, I don't know if you'll be able to see my mouse or not. Yeah, so you also have, you certainly have the growth in volumes. That's something that everyone is challenged with. But especially in heliophysics, we have the growth in variety of data. We have to be able to understand data coming from solar observing instruments, as well as instruments that are on the ground, maybe observing the ground magnetometer level, which you've probably heard a lot about this week. We have to be able to grapple with that. We have the growth in veracity of data. We have to understand how our data are not observing what we expect them to observe, or the uncertainties of those data, and allow them to be used together comprehensively. We have to understand those things. And then finally, something that's becoming more important in our field with the advent of and importance of space weather is the growth and velocity of data. How quickly can we process the information coming to us and generate new actionable insight from those data? And so this is the landscape, this is the drastically changing landscape that we're dealing with. And it's something that kind of presents a lot of challenges, but it also presents a lot of opportunities. And so I kind of organize these in 3 different sets of opportunities. The first is to evolve traditional approaches. So this is kind of the day in the life of a PhD graduate student, I think, and maybe a lot of you can relate to this, where 90% of our time is spent on wrangling data, which means going out, trying to find where those data are located, who is the authority on those data, what those data mean, and how we can download those and actually start to work with them. And then once we do download them, what's actually in those files. So we spend an enormous amount of time of data wrangling. Then we spend a lot of time staying up late, drinking coffee, and trying to do some analysis on those data. All of that to kind of carve out this little sliver of what we're actually trying to do is answer the questions that we're posing. We're creating new discovery from those. And so the traditional approach is to kind of do this in a one-off manner where we go through this data wrangling process over and over again, and we continually struggle with these things on our own. The way that we can evolve this is to start to embrace some new innovative technologies that allow us to accelerate that data wrangling process and grow the amount of time that we're spending on what we really care about, which is this discovery. And so that's what I think data science offers an opportunity for. So we need to embrace this data science-driven discovery. And I mentioned I wanted to demystify a few of these terms. And so data science is a buzz term, but I wanted to give the definition that I consider to be maybe the most insightful that I've heard. And it's given by a colleague of mine, Dan Crichton at the Jet Propulsion Laboratory. And he calls it scalable architectural approaches, techniques, software, and algorithms which alter the paradigm by which data are collected, managed, and analyzed. And I think I'd like to really emphasize this final point of collected, managed, and analyzed as the key clause in this. And really, data science has this bias of just being associated with machine learning. It's much more than that. It's the full data lifecycle where we deal with this data wrangling process that precedes any kind of advanced analytics that we can do on those data. So that's how I define data science and how I'll talk about it today. And then finally, we have the opportunity, as Lika mentioned, to really enable interdisciplinary work and communicate via the data and the methodologies. So I've talked about this in terms of heliophysics, but it really expands beyond that. And this meshes well with Lika's message that each of the fields across the NASA Science Mission Directorate is dealing with these same problems. And it's much more broad than that. Even fields outside of what we're studying in science deal with these drastically shifting data landscapes that we have to navigate. So I think that there are a lot of lessons and a lot of value that we can generate from data science and applying these. But how do we actually do that? And the way that I want to kind of approach that, and Andres will talk about some very specific use cases after this, which will fit in nicely with this. But I want to start with just a couple of examples of really fantastic use cases that are doing a nice job of embracing this full data life cycle. So I want to start with what I see as the data science project workflow. This is just kind of the way that I lay it out in my own mind and how I design some of my projects, and I thought maybe it would be helpful to share with you as you're going back to your research institutes and you're trying to rethink maybe how can I do this research differently. So the first step in this is to assess, and I would argue that this might be the most important step. We need to start with a well-defined, explicitly stated problem. We need to understand what exactly we're after. So when you talk about machine learning or artificial intelligence, it's very good at specific tasks. It's not good at general learning. It's not going to it's not going to come up with the problem for you and then answer exactly how you want the new discovery to be made. So we really need to spend a lot of time assessing the situation. What is the explicit goal? What data are available to us? What is the current state of the art, and what are the challenges that we're dealing with? So spending a lot of time on this will generate success and allow us to actually make discovery with some of these advanced techniques that we're talking about. Then we transition into a design phase. With this background and foundation of knowledge, we go to an ideation and prototyping process. And during the design stage, this is where we go into the data wrangling. This is where we start to get our hands dirty and bring those data together. We can accelerate this again by using some new innovative tools, but we develop potential solutions here and then we rapidly explore those. So the idea is not to spend all of your time thinking about the perfect solution and then trying to implement it. It's trying to go through all of the solution space or much of the solution space as fast as you can and trying to develop these techniques. And then I think a critical component of this is to visualize and explore your data in unique ways. Look at it in different ways and allow yourself to make smart decisions on how to design your project. As I mentioned, data wrangling is a significant component of this, so this process takes a while. After we've designed something that and experimented on it, we can kind of go into this analytical innovation phase. And so this is where a lot of people think data science exists. It's obviously much more broad than that, but this analyze phase exists with statistical and machine learning both. So try the techniques that are very simple, that go all the way through the spectrum to very, very complex, such as deep learning. But I do like to kind of clarify a few things about what machine learning is, just because everyone says it without necessarily knowing what it is. So there are a couple definitions that I like. One was by Arthur Samuel, just around 1960. And he calls machine learning a field of study that gives computers the ability to learn without being explicitly programmed. And the second definition that I like is more modern. It was given by Tom Mitchell just around the turn of the century in a really nice book. If you're interested in learning about some of the basics of machine learning in a good way, Tom Mitchell's book is really nice. But he calls it a computer program that learns from experience E with respect to some task T and some performance measure P if its performance on T as measured by P improved with experience E. And so you might need to read that a few times to kind of parse all of those things, but I think it really hits on some of the important points that I've been trying to make about the use of machine learning. So first, that machine learning is not just deep neural networks. It exists across a huge spectrum of techniques and algorithms that meet these qualifications. So everything from something that's very easily explainable, something that you can interpret very well, the support vector machine, across an entire spectrum of methods that increase in complexity towards deep neural networks, say, that are maybe more difficult to assign explanations to at the moment. One of the important points for what we're trying to do is we're trying to use these tools not for the sake of using them, but for the sake of the science dictates that we need some more complex approaches. And so we can create a narrative across these algorithms and these machine learning techniques that we can really build a new understanding for. So I think that with these definitions, we can illustrate that our success in machine learning depends on how well we define our task very explicitly, understand, populate, and manage the sample set, and then set up the means by which our performance is assessed. So this assessment of the model is really where our new discovery comes from. So after the analyze phase, a really critical component is feeding back that information that you learned through this assessment to reimagine what your problem is and allowing that to be an iterative process. And then finally, we move to deploy. We want to send these new developments out into the real world to be tested and improved as well. So the deploy process includes communicating the results, developing dashboards for people to approach those that maybe don't have the technical expertise that you do, and then also to automate those. And this is something that you can see a natural parallel with space weather, where we're trying to transition some of these heliophysics research components into operations. And then again, this is a feedback process where we can go all the way from the deployment phase back to the assessment phase. So these are the four phases, and I want to step through two specific use cases that I think well illustrate this data science workflow. The first one is more solar focused. It's a program that uses the Solar Dynamics Observatory instruments to study the sun, essentially trying to predict flares. So have you talked about SDO this week? Is everyone relatively familiar with that or not? Well, basically the Solar Dynamics Observatory sits between us and the sun, and at all times is looking and taking pictures of the sun. And so it's generating this immense view of the sun that we've never had before. And basically it's looking at the sun through all these different filters and providing more information than we've ever had to study the sun. So just a couple of pieces of information. It generates 70,000 full solar disk images per day. And during its primary mission lifetime, it's still going and sending back wonderful data that programs like the Frontier Development Lab are using. It generated almost 3 petabytes of data during that primary mission. So this is an enormous amount of information that we need to turn into insight and knowledge. So the program that I want to highlight is called the FlareCast program. It's something that emerged out of the European Union, and it's a consortium, a radically interdisciplinary project that wanted to use these solar images to develop new forecasting capabilities for solar flares. And so what they did was set up set up a project that analyzed this whole data workflow. They wanted to take away the data wrangling aspect from this and then make all the tools they were developing open so people could build on them. And so it was kind of this new approach to the problem that embraced these data science techniques. So what they did, some of the outcomes of this, they made a large volume of data much more discoverable. They focused on prediction, and so I mentioned the importance of knowing what you're trying to do. So they made it very explicit that they were trying to predict solar flares. And so they set their assessment. Are you able to hear me okay? This seems to be going in and out. Just goes in and out. I might just get rid of it and talk louder. Is everyone back hear me? Great, thank you. Okay, does that work okay for everyone? Okay, so they focused on prediction, which was a rigorous approach to this. With prediction, you know what the right answer is. You really have to get it right, and so it's a good way to metric the progress they were making. And then the last component that was a really nice lesson from this is that they had close collaboration with the solar physics and their data science communities, both in Europe and in the United States. So there's a really nice Flarecast website if you want to check that out. One thing that they did that was the lasting element of this in the deploy stage of their project was making all of their tools open source. They made an open source applied programming interface, and anyone can approach those, can build on those, can suggest revisions. And so that was something that was kind of unique at the time, and I think has been really impactful. And they've also put their flare forecasting capabilities on what's called the Flare Forecasting Scoreboard that's hosted out of the Community Coordinated Modeling Center, which is something basically where anyone who develops a flare forecasting technique can put their model up, and you can actually test how the different models are doing. So it's a really interesting ecosystem for kind of developing some new techniques. And it was a really cool outcome of this project. So the second use case that I want to talk about was the one that I led out of the Jet Propulsion Laboratory with the Data Science Working Group. And it was more Earth-focused. So what we did was tried to see if there was a similar data set in the near-Earth space that provided similar amounts of information as SDO was, and then to design a project that kind of emulated what the Flarecast program did for geospace. And the answer to that question was that yes, there was absolutely a wonderful data set that we could use, and it was generated by the GNSS systems. This is Global Navigation Satellite Systems signals. And so those signals are radio signals that are passing from, say, a GPS satellite and ground-based receivers. So anytime you pull out your phone and look up a map, you're communicating with a GPS satellite or numerous, and that's passing through the ionosphere, which is a medium between about 1,000 and 100 and 1,000 kilometers that is really an imprint. It's a screen for heliophysics and space weather activity. And so by studying the ionosphere, we can study this space weather interaction. And so we wanted to use those signals to try and predict when space weather would interfere with those signals, which affects all of the services that rely on those signals to operate, which is essentially everything in our day and age. So we called this Stretching GNSS Signals for Space Weather Discovery. And just a quick comment about this is, I mentioned the need to bring together these diverse teams. So our team for this project was wildly diverse. We had myself and Tony Minucci, who study the space environment. But we also had Brian Wilson, who was an Earth scientist. Chris Madman, who was the principal data scientist at the Jet Propulsion Laboratory, was a contributor to this. Sujin Shah is a computer scientist. And then Hyokyo Lee kind of straddles the boundary between Earth science and computer science. So it was a really radically interdisciplinary team that was able to come together for this work. But what do these pieces of information look like, and how do we utilize them? So these signals, as I mentioned, are communicating through this region of the ionosphere. And what happens is as they pass through the ionosphere, they are affected by the composition of the ionosphere. So based on that signal delay, we can infer really important properties about the ionosphere, such as the total density, the total electron density of the ionosphere. And this can be useful across the domain space of space weather. But what happens is when we have a solar event or any kind of activity that's causing changes in the ionosphere, we get these disruptions. We get these pockets of density or irregularities that when a signal encounters them, it can be disrupted in some way. Either it's completely lost or redirected and modified in some manner. And so that's called scintillation. And it's a very complex problem because these irregularities they exist across a lot of different scale sizes, both temporally and spatially. They move with different speeds and for different reasons and are forced by different things. So there's a vast, complex set of phenomena that are controlling the location and existence of these irregularities. And so trying to quantify that is a very difficult problem. And the data set that we have available to us, these GNSS signals, is perhaps the best capable data set to study this problem. And the reason for that is that it covers a more global area at a higher temporal cadence than any other individual data set that we have. And so what I've illustrated here is just a 2-hour time window of the location where each of the GNSS systems signals are passing through the ionosphere. And so at the top you'll see the US system, the GPS signal. In the middle is the Russian system, GLONASS, and then at the bottom are the continually updating Beidou and Galileo systems in China and Europe, respectively. And so you can see that this 2-hour snapshot really provides you essentially a global view of this ionosphere. And so we can use these signals to start to develop new understanding around these. And so that was kind of our assessment stage. We wanted to use these signals to predict scintillation. The next we moved into the design stage. And so we wanted to use machine learning to do this process, or some advanced techniques to do this process. And so with machine learning, there are a number of different problems that are well suited to this. And this is what we went through with this design stage, where we start, classification is one that I think is a pretty commonly used application of machine learning. Event detection, segmentation, clustering, when you take these data and you want to understand the categories that they may fall into. For this work, we took a similar approach as the Flarecast community and developed a prediction approach, trying to predict when scintillation would occur at some time in the future to protect the integrity of those signals. And then again, with this design phase, we wanted to examine a narrative across the spectrum of machine learning algorithms. And so with this project, we did analyze all these. Today, I will focus on the support vector machine as an example. Happy to point you to some resources that we produced for this work, or talk with you offline if you want to talk about some of our work towards random forests and neural networks as well. So with the design stage, I've divided this into the 4 steps that we took to look at this. The first was to obtain the data, to do this data wrangling process. And so to do this, we really realized we needed information from every step between us and the sun. And so we looked at the solar information, the geomagnetic information, and data from the ionosphere. And so from each of these regions, we brought information into the problem. To study the ionospheric component of this, we used a specific set of ground-based receivers in the Canadian sector known as the Canadian High Arctic Ionospheric Network, or CHAIN. And so this is a selection of about 25 ground-based receivers that are communicating with these GPS satellites and generating that information about the ionosphere. And so we wanted to use those to develop this predictive tool. And again, we set very specifically our task was to predict when scintillation would occur at some time in the future. But then we started to look at the algorithms that we could use to do this. And I'll illustrate just the support vector machine as a very simple approach to this. So we can think of the classification problem as a pretty simple problem in 2-dimensional space. So think about having electron flux in the solar wind and interplanetary magnetic field in the solar wind as 2 parameters of your input space. And so with each sample, each data sample, you'll have information on the electron flux and the IMF, and you'll have some label, whether or not scintillation was observed on that signal. And so with that, you can separate these samples. And the idea with the support vector machine is to identify the boundary that perfectly separates them. So at some time in the future, when you have this information, you can then make a prediction on whether or not scintillation will occur. And the way that the support vector machine does that is by identifying the samples that are most difficult to classify, or the support vectors, the ones that exist closest to this boundary. And then it tries to optimize that margin. And so that's the approach that I'll demonstrate today that we used for this. And at this point, we have kind of completed our design phase, and we move into the analysis phase. And to analyze this, we used a range of robust metrics, all of which kind of spring from this idea of a contingency matrix. The contingency matrix lays out essentially how well your model's doing in terms of prediction. So to introduce it, on the left we have the true label, and on the bottom we have the predicted label. So if no scintillation is observed in the data sample and no scintillation is predicted, we'll get a true negative, and that means your model is correctly predicting that no scintillation occurs. On the alternative case, if scintillation is both observed and predicted, we get a true positive. So we really want to optimize this diagonal of this contingency matrix here. The false positive and false negative represents cases where your model does not understand or does not correctly identify the physical situation. So just quickly, the results from this, we found this with our model using 2 years worth of chain data. We found that we had a 91% accuracy in improving the ability to predict when scintillation would occur, and it indicates the potential of the approach that we developed. This is gauged against basically no predictive capability before. So the current state of the art in predicting ionospheric scintillation is using climatology or persistence, which are pretty crude ways of trying to predict scintillation. And so we developed this new potential. We found a relatively high accuracy of predicting when scintillation would not occur. I do point out that we had about a 33% chance of predicting when scintillation to occur when it actually did not. And so this represents kind of looking at the model and understanding there are cases, a number of cases where we have false alarms. And so how does that feed back into our design process to improve moving forward and kind of develop a more capable model? And that's the fourth step in this. And this is the one that I think is really critical, that's often overlooked in these approaches to machine learning. I think a lot of people develop a model, get to a level of accuracy, and then just say, okay, we've developed that capability, and they move on. The new discovery in science, and where we really need to place our focus, is in assessing and really interrogating our model and trying to open it up and understand what exactly is happening. That's where the new discovery comes from, and often where I see some studies in machine learning kind of fall short of the application. And so that involves interrogation. And so just to illustrate what we did for interrogation, just one technique is to try and bring in physical information into that problem. So we looked at novel data from space weather events and tried to understand how our model was predicting those situations. So basically, don't want to belabor the details here, but this is just a geomagnetic storm that occurred on January 20th, 2016. And these are a couple parameters from the solar wind and geospace that indicate there was a large amount of activity in the middle of the day. On the top here is essentially, this is a parameter that tells you how disrupted that signal is, so what the level of scintillation was. We set our threshold at this dashed line, and any signal, any point that falls above that line represents a scintillation case that would affect that signal or a service operating with that signal. And so we want to predict all of those cases. And so basically on the middle, we're looking at the prediction of our model, and on the bottom, we're looking at the state of the art, the persistence. So basically saying whatever conditions exist now are what are going to exist in the future prediction time. And we've laid out these components and color-coded to the contingency matrix. And what you see are a few things. First of all, at the middle of the day, when we have these strong scintillation signals, the support vector machine is identifying that strong scintillation correctly, but the persistence is not. We also said, as before, we have these high number of false alarms that are occurring right when the signal is close to this threshold of classification. And so that provides us with information that we can then feed back to a new design process on what new information do we need to more appropriately classify those fringe cases, and how can we design our system to better approach that, and for what reasons are we incapable of predicting those? And so that represents the feedback process. So finally, with the deploy process, with this project, we developed an open source tool. We have all of the code that we developed around this. Put those online on Figshare that you can look up and build on and improve. And we developed a challenge data set. We actually provided the data so that you can immediately go experiment with this without going through the data wrangling process. And I think that this being open by default, putting all your information out there and putting all of the things that you develop out there is a critical component of kind of this new frontier. And then we also extended this work and amplified this work with the Frontier Development Lab with a program last summer that I mentored on, and it's been actually grown into a new program this summer as well. So finally, to bring this full circle, I want to talk about how we can shape the new frontier. I think this will lead nicely into Andres' talk as well. So I mentioned that we exist in this ecosystem where everyone is kind of dealing with these challenges. And it offers an opportunity for us each to kind of come together and communicate via methodology transfer. And so the last opportunity that we have with this is to enable interdisciplinary work. And you kind of see ideas about this springing up across everything that we were paying attention to. So one is with the National Science Foundation. They have a set of 10 new big ideas that they're pursuing as what they see as painting the future for scientific discovery and engineering discovery. And one of those is called Convergence. And they title Convergence as the integration of knowledge, methods, and expertise from different disciplines informing novel frameworks to catalyze scientific discovery and innovation. So there's a lot of actual solicitations out now that we can apply to get funded to do this interdisciplinary, non-traditional kind of work. And then finally, to introduce this anti-disciplinary term that I've been talking about, I got this from someone I think is kind of doing the most original thinking in this space. His name's Joey Ito, and he's the director of the MIT Media Lab. And he calls anti-disciplinary someone or something that doesn't fit within traditional academic discipline, a field of study with its own particular words, frameworks, and methods. And I just think that that's a really inspiring definition and kind of way of thinking about this that I recognize kind of reverberates across my career as well. So to move towards anti-disciplinary, I just wanted to leave you with a message of kind of encouraging how this is being done and how you can get involved. So there's a lot of efforts going on in this space, like space weather workshops at the Lens Center. There's a Helio ML workshop that's coming up in September in Amsterdam that you can look at. We're leading an International Space Sciences Institute project that really is looking at this whole data science workflow for space science, and if you want to talk about that, I'm happy to. With Lika and a number of people in our communities, we're cultivating this community that's radically interdisciplinary and kind of pushing these data science initiatives. And so there's a lot of opportunity to get involved there. And I think each of you kind of have a unique opportunity to take your knowledge from this week and kind of the things you've been thinking about and move forward and be pioneers of this new frontier in each of your own networks. And I think it's a really interesting, fascinating space. And so I hope that you will be a part of this, shaping the new frontier. You'll reach out to me if you have any questions or, it's just something I'm passionate about. So if you want to talk about it. So the final messages are just to make sure you understand your models, really interrogate them, be open by default and collaborative by default, and be radically interdisciplinary. So thank you very much. Great. Thanks.
Take just a short break, come back.
Andres, good to see you. Very nice. Hi, my friend.